Hello everyone, and welcome to the Physics 213 lab exam review. This is for lab exam 2. So what I want to do in this review is give you at least an idea of the type of questions that will be on the lab exam. I'm not going to do an exhaustive review, but I'll give you a good sense of the type of questions that you should expect for the lab exam. Okay, so starting off, there's going to be several circuit type problems, right? So we have the circuit. And let's say we're given some information about this circuit. Let's say we're told, first thing I'm going to do, this is a little confusing. I accidentally used the wrong subscript here. Let me call this I2, since I call it R2, so I2 is the current flowing through that resistor, and let me call this one I1. That'll at least make it a little easier when we're thinking about this. Let's say we're given the fact that I2, that current, is 0.006 amps. And we're also given the voltage across the battery, which is delta V here. Let's say that is like 33 volts, that voltage source. So given that information, we want to find I1. So that's this current, right, going through this resistor R1, and we also want to find R1. So we want to find I1 and R1. Okay, so first thing that you should recognize is this is a series circuit, right? It's a series circuit. So we know that the currents stay the same. Right, whatever current goes through this resistor goes to this resistor and goes back through the battery. So I total equals I2 equals I1. So if we know I2 is 0.006, then I1 must be the same, right? So I1 is equal to 0.006 amps. So that's the first question, right? That's done. What else? We also know if we have a series circuit that the voltage drops will add, right? Basically, the voltage that you gain across the battery is going to be equal to the voltage drop across the first resistor plus the voltage drop across the second resistor. So I can say that, in this case, delta V, I'll call it delta V total across the battery, total. That's equal to delta V across the first resistor plus delta V across the second resistor. So this is really delta V across the first resistor, right? Delta V1, and then this is R2, so this is delta V across the second resistor. Now, since I have the second resistance value, right, R2, I can figure out that voltage drop across that resistor. I can figure out delta V2, because I know the current going through it, and I know the resistance value itself, right? So using Ohm's law, we know that delta V2 is going to equal I2 times R2. Right? Delta V is I times R. So in this case, I2 is 0.006 and R2 is 3000. So that's going to be 18 volts. Okay, so this is really equal to 18 volts here. All right, now that I know that, remember across the battery is 33, right? We're given that. So I can find delta V1, right? I can solve this equation now for delta V1. If I know delta V total, let me write it one more time. Delta V total is delta V1 plus delta V2. So delta V total is 33. Delta V1 I can solve for, I'm looking for that, and delta V2 is 18. So basically, I'll subtract 18 from both sides. And I'm going to get delta V1 is equal to 15 volts. Okay, and then finally, to get what I really want, which is R1, so I'm going to get that resistance value. Again, now I know the current passing through, I know the voltage drop across. I can use Ohm's law, which relates those three variables together, to figure out R1. So normally, right, we'd write I1 equals delta V1 divided by R1. But if I rearrange this, I can write it as R1 is equal to delta V1 divided by I1. In this case, this will be 15. I1 is 0.006. And if you work that out, it turns out the resistance is 2,500 ohms. Okay, so that would be R1, 2,500 ohms. Okay, in this question, we're given another circuit. In this case, it's a parallel circuit. And let's say you're told that this voltmeter reads a particular value. In this case, let's say it reads 19 volts. So this is 19 volts, right? Which means that this resistor, let's call this, I'll call this R1. I'm going to call this R2. Actually, let's assume we have to know their values. Let's assume they're both 20 ohms. So this is 20 ohms, and this is 20 ohms. Then that means delta V2, right, the voltage drop across that second resistor is 19 volts, right, because I'm measuring that directly. Now, because that this is a parallel circuit, that means the voltage across the battery, delta V total, is also 19 volts, right? And also the voltage across the first resistor is 19 volts. Okay, our goal is to figure out the current right here at this location. What is that current that would be read by the ammeter there? Okay, if you want, you can think of this as like I total. Right, that would be the current passing through the ammeter. So the way to solve this is to really probably combine those two resistors together to form a simple circuit. And then once we have a simple circuit, we can use Ohm's law to figure out that current, right? So if I draw this as a simple circuit, I still have my battery here. And then I'm going to replace, I can draw it anywhere, I'll just draw it like this vertically. I can replace those two resistors in parallel with a single resistor. So what do I know? I know delta V total is still 19 volts. I have to figure out R total, right, this new equivalent resistor, and I want to calculate I total, which is flowing through here, I total. Okay, well, those two resistors were in parallel, right? So we know that if they're in parallel, the equivalent resistance value is going to be R1 times R2 over R1 plus R2. So in this case, they're both 20, right? So this is going to be 20 times 20 over 20 plus 20. So this is 400 over 40, which is equal to 10 ohms. So this R total is really just 10 ohms. Okay, now that I have that, I can calculate the current I total just by using Ohm's law. So I total is going to be delta V total divided by R total. So this is 19 divided by 10, and that is equal to 1.9 amps. So this meter here, this amp meter, must be reading 1.9 amps. Okay, let's do one more circuit problem. Okay, in this problem, let's say we're given the battery, right? I'll call this delta V total. Let's say that is 50 volts. And we want to find what the voltage meter is reading across that second resistor there. So I'll put a question mark. Okay, you can think of this as like, delta V2. What is that voltage reading across the second resistor? So how do we answer this question? Well, if we could find the current, first of all, this is a series circuit, right? If we could find the current going through all these resistors, remember in series it's going to be the same current. then I could just multiply that current by the resistance value R2, which is 10 ohms, and that will give me what I want, which is a voltage drop, right? Again, if you label these, think of the 5 ohm. This is like R1, this is like R2, this is like R3, okay? And we want to basically find like I total, the current going through the battery, but that's going to be the same. It goes through all of them, right? Because it's in series. Okay, so to do this, let's draw an equivalent circuit. An equivalent like simple circuit. And I'm just going to put a single resistor there now, right? I'm going to combine those 3 resistors in series to have a simple single resistor. So again, delta V total is equal to 50 volts. We know that. And then how do I add, this is I total. How do I find R total, the equivalent resistance value, if I combine those 3? Well, remember, if they're in series, you simply add, right? So R total is going to be R1 plus R2 plus R3, which in this case is what? It looks like it's 20, right? So this is going to be 20 ohms. So now using Ohm's law, I can find I total. I total is going to be delta V total divided by R total. So this is 50 divided by 20. What's that? 2.5, I guess, right? 2.5 amps. So I know that since it's a series circuit, 2.5 amps is going through here, right? R1, 2.5 amps is going through R2, 2.5 amps is going through R3. But I want to find the voltage drop across R2. So again, using Ohm's law, right, I can say that delta V2 is equal to I2, which is I total. That's the current, is the same current going through all of them, times R2. So this is going to be 2.5 times 10. And that is equal to 25 volts. Oops, 25 volts. Okay, and actually you could have found all these voltage drops, right? If you found the voltage drop across this 5 ohm, that would be, I guess it would be like 12.5, right? This is 25, this is 12.5, and they add up to a total of 50 volts, so that makes sense. Okay, in this example, we have a standing wave that was set up in the resonance tube, right, with the open air speaker. And let's say that these nodes, so remember there's a node at the barrier, in this case a node here, a node here. Let's say the locations of those nodes are, A is at 80.1 centimeters, B is at 48.1 centimeters, and C is at 16 centimeters. And given that information, I want to find the wavelength, right, in meters, and I want to find the speed of sound, which I'll call it V, and that's going to be meters per second. Okay, what am I given? Well, I'm given the locations of those nodes. Let's say I'm also given the frequency that the speaker vibrates at. So let's say the frequency F is 546 hertz. Okay, so given that information, I want to find the wavelength and then the speed of sound. So first thing I would do is figure out what the node-to-node distance is, right? So remember, the node-to-node distance is basically the distance from one node to the next node, right? Node-to-node distance. So to do that, I can basically subtract these two values, right? And then subtract those two values. And they should be the same or very, very close. There might be some rounding error here. So if I do that, so we'll let S equal the node-to-node distance. So like the first one, S1, is going to be 80.1 right, centimeters minus 48.1. And that equals 32 centimeters. And the second one, I'll call S2, is 48.1 minus 16, which is 32.1 centimeters. Now, ultimately, we're going to want meters, so I'm just going to convert these to meters. So this will be 0.32 meters. I had to move the decimal 2 places to the left, and this is 0.321 meters. Okay, so let's average these node-to-node distances. I'll just find the average of S1 and S2. So this is going to be S1 plus S2 over 2. And actually that turns out to be, I guess it'll be 0.3205, right, meters. Okay, now remember that a wavelength is equal to twice the node-to-node distance. So if I multiply my average node-to-node distance times 2, that's going to give me the wavelength, right? So 2 times 0.3205. In this case, that will be 0.641 meters. Okay, so that's my wavelength. And then finally, if I want this, the velocity of that traveling wave, which is really the speed of sound, in general for any wave, remember the velocity is the frequency times the wavelength. So if I give you the frequency as 546 hertz, and we multiply by 0.641, that ends up being right around 350 meters per second. So that would be the speed of sound. Okay, in this question, so this is the lab where we looked at the standing waves on a string. So let's say we're told, again, we're given some information, right? We're told that the length from the blade to the pulley, let's say that length was 0.87 meters. Okay, so that distance is 0.87. Let's say that the blade was vibrating at a frequency, so the frequency here, F, is, say, 63 hertz. Right? So it's oscillating 63 times a second. Let's say we're also told the linear mass density of the string, so remember that was called mu, is 0.008 kilograms per meter. And we want to find the tension in the string. We want to find lambda, right, the wavelength, and then we want to find the wave velocity, meaning the wave velocity of the traveling waves that make up the standing wave, right, the ones that travel to the right and reflected travel to the left. All right, so let's start with the wavelength. So the wavelength, remember, is going to be 2L over N. We derived that, right, in lab, where L, in this case, was the length from the blade to the pulley. That's 0.87. And then remember, N represents the number of loops that you're observing. So in this case, we're observing 2 loops, right? So this is just 2. So obviously the 2's cancel. So in this case, it's just going to be 0.87 meters, right? That would be the wavelength. All right. Let's do the wave velocity next. So wave velocity. Well, that was F times lambda, right? So as a formula I could write is 2FL over N. So that'll be 2 times the frequency, which was given as 63, times L, which is 0.87, again divided by the number of loops that you're observing, which is 2. And that ends up being 54.81 meters per second, right? So that would be the wave speed. And then finally, we want to compute the tension in the string. Remember, we derived that formula as well. Now remember, it was 4 mu f squared L squared over n squared. So this would be 4, mu is 0.008. The frequency was 63 hertz, right, squared, and the length is 0.87 squared, all divided by 2 squared, right? Number of loops that you're observing is 2. And if you work that out, you're going to find this is it's 24.03 newtons. All this around, 24.0 newtons. I'll do 2. 24.03 newtons. Okay, so I could ask you some questions about that, about wave motion and sound. Yeah. All right, let's move on and look at some of the type of problems that could be on there from optics. Okay, so in this question we have a ray of light coming in, or you can think of it as a laser beam, and then so it's in air to begin with. Then we have this glass prism. When it hits the boundary, it refracts, right? So it bends, goes through the glass prism, and then when it hits the air again, goes from glass to air, it refracts again, in this case refracting outward, and goes this way. So let's say we're given some information. Let's say we're given that this angle, phi1, is 55 degrees. So phi1 is 55 degrees. And let's say we're given R2 over here is 41 degrees. Okay, and the goal here is to calculate N glass. So I want to find N glass, what that value is. All right, so first thing, in order to do that, since I'm given this value, I'm given R2 is 41, if I can figure out I2, then I could use Snell's law, right, on this face, the second face, and that will allow me to figure out N glass. So I need to figure out I2. Well, in order to figure out I2, I first need to figure out phi2 here. But what do we know about a triangle? All the angles must add up to 180 degrees, right? So for triangle, we know that we have 60 degrees plus phi1, which is 55 degrees, plus phi2, that's got to add up to 180. Okay, so in this case, this is what, 115 plus phi2 equals 180. So if I subtract 115 from both sides, then it looks like phi2 must be, I guess it's 65, right, degrees? So now we know this value, phi2 is 65 degrees. Okay, now remember, when you measure angles, it's always measured with a perpendicular to the face. So that means that phi2 and I2 must add to 90 degrees, right? So phi2 plus I2 must be 90 degrees. So phi2 plus I2 equals 90 degrees. So that will allow me to figure out I2, because again, I know phi2 now is 65. If I subtract 65 from both sides, I'm going to get I2 is, what's that, 25 degrees. Okay, so I2 is 25 degrees. Now I can use Snell's law on the second face here. Right, remember Snell's law says if I take the index refraction of that first material, so think of it as you're starting in the glass, right, starting in the glass, hitting the boundary between the glass and the air and going into the air. So starting in a glass, going into air. So Snell's law is going to say N glass, right, index refraction of that first medium, times sine of the angle, which in this case, the angle is going to be I2, must equal the index refraction of the medium you're going into, N air, times the sine of the refracted angle, in this case R2. So if I solve this for n glass, I'm going to find n glass is equal to n air times sine of R2 over sine of I2. Well, n air is basically 1, right? Sine of, well, we know R2 was 41 degrees. And we just found I2, which was 25 degrees. And if you work that out, you're going to find it's like 1.55, which sounds reasonable because remember glass has an index of fraction around 1.5 something. So that sounds reasonable. Okay, in this problem, we have like our optic bench, and we have our light source, right, the object. We have the lens that's in the lens holder in the center, right? So lens here, object here, and then on the screen, that's going to be where the image is projected. And let's say we're given some information. So we're given the distance from, remember DO is a distance from the object to the lens. Let's say that is 40 centimeters. And then DI is a distance from the lens to the image, to the screen. Let's say that is 41 centimeters. And what we want to calculate, let's say the lens in here is a converging lens. Remember, that's going to be a double convex lens, right? It'll look like this if you look on the side. Double convex, so it's a converging lens. So we want to find the focal length of that converging lens. So I'll call it F converging. And then let's say we also want to find the magnification. Let's say I'll just call it M for magnification. Okay, so how do we find F converging? Well, we can use the thin lens formula, right? So this says that F converging is equal to di times do over di plus do. We derived that in lab. And in this case, this will be 41 times 40 over 41 plus 40. Right, so that'll be 20.2 centimeters. So that's the focal length of that converging lens. And then for the magnification, remember there's two ways of doing it. You can measure the actual objects. So you can measure the object, measure the image, and it's a ratio of the image to the object. However, there was also a formula for this, right? Geometrically, it turns out it's also just negative. The negative means the image is flipped. So that's why over here, if you look at this, see how the arrow is upside down, right? The original one is up, this is upside down, so it's flipped. And then if we want the magnification, it's negative di divided by do. So in this case, it'd be negative 41 divided by 40, which is like negative 1.025. So in other words, it's almost the same size, it's slightly larger, and it's flipped. The negative tells you it's flipped. Okay, in this example, we're given a, we're going to think of it as a concave mirror, all right? And let's say we're told that the radius of curvature of that concave mirror is 7.5 centimeters. And if we have light coming in, again, it's the concave side, right? So light comes in this direction. In this case, right in the center, it's going to bounce off and go right back. And then if light is coming in parallel, so like that somehow, it's going to somehow reflect, right, with the angle of incidence equals the angle of reflection. And these rays should all meet at one point. Remember, this is called like the focal point of that concave mirror. And we want to calculate the focal length of that concave mirror. The focal length is just the length from here, right, the focal point, to the vertex, like the center of the mirror here, F. So remember in this simple case, when you have a concave mirror, the focal length is just half the radius of curvature, right? So really that's all you need to do. So the focal point here is going to be r over 2. So in this case, it would be 7.5 divided by 2, which is what, 3.75, right? 3.75 centimeters. So that would be the focal length of that concave mirror. Okay, so for the last question, let's say that we're given two charges. We have one charge that's 8 nanocoulombs and it's at the origin at 0, 0. We have a second charge that is -1 nanocoulombs. It's at 0, y, and we're going to say y in this case is 2.5. So 0, 2.5, and those are distances basically in meters. So this y here is 2.5. And then we want to find the total electric field, right, the net electric field at 2, y, where that yellow dot is. So in other words, we want to find the total electric field at 2, 2.5 at that location. Okay, so to do this, right, remember you have to use superposition, right? You have to find the electric field due to each charge separately, put them in both in vector form, and then add them together. And when you add them together, that'll be the total or net electric field. So just to get an idea of what's going on here, if this is Q1, right, at 0, 0, and I want to find an electric field at 2, 2.5, since that's a positive charge, we know the electric field is going to be pointing away from the charge, right? So at that location, the electric field is going to look something like this. Right, so this is like E1. And then the blue charge, first of all, it's much smaller, so Q2 is -1 nanocoulombs. And for that electric field at this location, 2, 2.5, it's going to be pointing towards the charge, right, back towards the charge. So it'll look something like this. So this is E2. And I basically want to find E1, E2, add them together, and then basically put it in polar form, right, find the magnitude and direction. Okay, so let's start with E1. So to find the magnitude of E1, that's got to equal K times absolute value of Q1, right? This is a Q1 here, divided by R1 squared, right? That would be the magnitude. That would be the length of that vector. And how do we find R1? Well, R1 is basically this distance, right? It's the distance from here to the point at which I want to find the electric field, so at 2, 5. So if you think about it, what I would do is maybe construct a right triangle here. And we know this distance, the horizontal distance, is going to be 2, right? 2 minus 0 is 2. And then the vertical distance is, I guess, 2.5. So this distance, which is R1, is going to be the square root, right, of 2 squared plus 2.5 squared. And that turns out to be like 3.202 meters. So this is equal to 3.202 meters. Okay, so the magnitude of E1 is going to be K, which is always 9 times 10 to the 9th. And then absolute value of Q1, well, Q1 is 8 nanocoulombs, right? So this is 8 times 10 to the -9th, divided by, and then R1 is like 3.202, and I need to square that. And if you work that out, this turns out to be 7.02. Right, volts per meter. Okay, but what I really want to find are the components, right? So if I project this, let me continue. Let's say this is the y-axis, right? This is the x-axis. If I project this vector onto the x-axis, this is going to be like E1x. And if I project it onto the y-axis, this is going to be E1y. So to find those, I need to use trig, but first thing I need to do is I need to figure out what this angle is, right? This angle theta here. But that's the same as this angle theta here, right? Those angles are the same. And I can definitely find this one because I know the length of the opposite side, I know the length of the adjacent side. So using inverse tangent, I can find theta. So it's going to be inverse tangent of opposite over adjacent, and that turns out to be 51.34 degrees. Okay, so now if I want to find the components of E1, then first of all, they're both going to be positive, right? E1x is pointing to the right, E1y is pointing up, so they're both going to be positive. To find E1x, that's going to be E1, the magnitude of E1, which I already found, times cosine of that angle theta. All right, so in this case, it'll be 7.02 times cosine of 51.34 degrees. And that turns out to be around 4.39 volts per meter. And then E1y is going to be E1 times sine of theta. So that's going to be 7.02 times sine of 51.34 degrees. And that turns out to be 5.48 volts per meter. Okay, so now I can write the electric field right at the yellow location, right at 2, 2.5, due to charge 1, Q1, it's going to be equal to 4.39 I hat plus 5.48 J hat, right, volts per meter. Okay, so that's E1. Now I got to go back and figure out E2. Well, E2, to find its magnitude, it'll be K times absolute value of Q2 over R2 squared. Right, K is 9 times 10 to the 9th. Absolute value of Q2 is going to be 1 times 10 to the minus 9th, right? It was 1 nanocoulomb. It was negative 1 nanocoulomb, but I'm just doing absolute value here. And then R2 in this case, that's not so bad, right? That's going to be this distance, which is just 2. So this is divided by 2 squared. And if you work that out, that's going to be 2.25 volts per meter. However, the direction of E2 is to the left, right? It's pointing exactly along the negative x-axis. So written as a vector, E2 is going to be negative 2.25 I hat, and then plus, there's no y component, right? 0 j hat volts per meter. Okay, so now I can actually combine these, right? I can add these together. So E total is E1 plus E2. So that'll be 4.39 I hat plus 5.48 J hat plus, and then this is going to be negative 2.25 I hat plus 0 J hat. So I need to add the x components together, which basically means add the I hats together. And if you do that, you're going to get 2.14 I hat. And add the j hats together, that's just going to be 5.48, right? Plus 0 is just 5.48. Okay, so that's my answer, but it's in component form, right? I want to find, actually, I want to put it in polar form. I want to find the magnitude and the direction. So to find the magnitude, E total, I can use Pythagorean theorem. First of all, they're both positive, right? So I'm in the first quadrant. Like if you were to plot this, E total is going to be somewhere in the first quadrant like this. It looks like the x component is like 2.14, and the y component is 5.48. Right, and we need to find the angle too. So we need to find the length of this, the length of that vector. To do that, we can use Pythagorean theorem. So E total is going to be the square root of 2.14 squared plus 5.48 squared, right? Square root of the whole thing. And that's going to be 5.88 volts per meter. And then finally, I need to find the angle. I'll call it phi. Well, this is nice. Again, it's in the first quadrant. So phi is going to be inverse tangent of opposite, which is like E total y, 5.48, divided by adjacent, which is E total x, 2.14. And if you work that out, you're going to find it's 68.7 degrees. So this is the answer in component form, right? With I hat and j hat, x component, y component. And this is the answer in polar form. That's the magnitude, and this would be the direction. And it's just north of east. I don't have to put that because I'm assuming I'm measuring from the positive x-axis, right, counterclockwise like that. So that is that angle, 68.7 degrees. All right, great. So hopefully that will give you a good idea of the type of problems that will be on this second lab exam. Thanks.